Hi there. Welcome to today's lecture. This is lecture number 2 in the series of lectures on vectors. Today we are going to learn about vector addition and subtraction, a very important topic. Why so? Because like we have discussed in the previous lectures, there are several physical quantities that are vector in nature, and these physical quantities and the parameters representing them, they interact with each other. And since these quantities are vector quantities, when they interact with each other, they can add and subtract. Just like before you learn how to read words, before you learn how to read sentences and books, you must learn the alphabet. So think of this as the alphabet. Before you can really dig deep into physical concepts, we must first learn these basic foundational things, such as vector addition and subtraction. Alright, are you ready? Well, I sure hope so. Let's do it. So here we have this cute and sweet little kiddo who's super duper excited. Why? Because he is about to go to the zoo. Let's call him Tom. He steps out of his car onto the ground and now he's going to walk to the zoo. To walk to the zoo, he takes this path. He first goes 8 meters due east. Then he goes 5 meters up north and then 10 meters east, then 5 meters down south, and then 6 meters to east. So path from Tom's car to the zoo, it consists of 5 straight line segments, D1, D2, D3, D4, and D5. Now you may have noticed these straight line arrows on top of these D's. What do these arrows mean? I bet you know what they mean. They mean that these D's, these are vector quantities. And vector quantities, like we have discussed before, they are physical quantities that have both magnitude and direction, unlike scalar quantities that have only magnitude and no direction. So in this case, in this example over here, Tom is going from his car to the zoo along 5 straight path segments. So here's the question for you. What is the total distance traveled by Tom to go from his car to the zoo? So like you know, distance is a scalar quantity. It is sum of all the path elements to go from some initial position to the final position. So here in this case, the distance traveled will be the magnitude of D1 plus magnitude of D2 plus magnitude of D3 plus magnitude of D4 plus magnitude of D5. So that is 8 plus 5 plus 10 plus 5 plus 6. And what does this give us? This gives us 5 plus 5 is another 10. And that 10 and this 10 is 20. 28 here. 28 plus 6 is 34 meters. So Tom travels a distance of 34 meters to go from his car to the zoo. But if we talk about the net displacement, now net displacement, it is a vector quantity. That means in addition to magnitude, it also has direction. It is the straight line to go from initial to the final position. So in this case, displacement will be this line segment over here. Alright, so this is the displacement. To get this displacement, what we can do is add up all the individual displacements. And this is an example of vector addition. And when we add all these individual displacements, D1, D3, and D5, these 3 are along east. So they are going to add up to each other. While D2, which is going up, and D4, which is going down, they are equal in magnitude but opposite in direction. So D2 and D4, they basically cancel each other out. So the net displacement, that is going to be 8 plus 10, 18 plus 6, that is 24 meters. Here you go. This was a simple, sweet, and cute little example of vector addition. Taking it a bit further, now we're going to pull out D1 and D5, and these are both due east. What are we going to do with them? We are going to add these two displacements, D1 and D5. They're both going east. So here D1 and D5, they're both going to right, or they're both going east. So here we can choose east or the right direction to be the positive direction for displacement. So that means any displacement that is being made to the right or to east is going to be a positive displacement, while any displacement that is made to the left or west is going to be a negative displacement. So this example, it is very simple, very easy. D1 and D5, they're both going to the right. Therefore, they're both positive displacements. 8 plus 6 gives you 14 meters. That is your answer. Here you go. Easy? I think so. Moving on. Now we're going to look at vector subtraction. We want to subtract here D5 from D1. D1 is to the right, D5 is to the right. Now, let me remind you something here. If you want to subtract 2 from 5, okay, these are both positive numbers, right? 5 is a positive number, 2 is a positive number. Instead of subtracting positive 2 from 5, could I say add negative 2 to 5? Sure can. These are both same things, and they're both going to give me 3. So here, in case of this vector subtraction, in place of subtracting D5 from D1, what I'm going to do is I'm going to say I want to add negative vector of D5 to D1. In other words, this is what I'm saying. Instead of doing D1 minus D5, what I'm going to do is I'm going to say, all right, this is my D1. I'll keep it the way it is. To that, I'm going to add negative vector of D5. Now, what's the difference between D5 and minus D5? The only difference is the direction. The magnitude of D5 and minus D5, these are negative vectors of each other, is going to be the same. By the way, we went over negative vectors in the previous chapter, in the last chapter. And not just negative vectors. We went over all different kinds of vectors in the last chapter. If you haven't watched that lecture yet, I strongly recommend you that you watch that lecture. You know what? I'll give you a link for that lecture in the description for this lecture. All right, back to this. So D5 and minus D5. These are negative vectors of each other. That means they're going to be exactly equal to each other in magnitude, but opposite in direction. All right, very well. So this is what we're saying. Instead of subtracting D5 from D1, add minus D5 to D1. And if you have noticed, minus D5, it is going to the left. Okay. And when we do so, 8 minus 6. This minus here has only one meaning, and that is the direction. So this one here, up here, which was D5 equal to 6 meters, the length of this, let's say this is 6 centimeters or 6 meters, then the length of D5 is also 6 meters. These are both equal in length. This minus here means that minus D5 is going to the left. And that is the only significance of the minus sign in case of vectors. And when you add 8 to minus 6, what do you get? 2 meters. So here's your 2 meters, D, going to the right. This is vector subtraction. So here you go. Vector subtraction. It is nothing but the addition of the negative vector. So in place of subtracting, what you could do is take the negative vector and add it. That means if you are to subtract V2 from V1, then in place of subtracting. Take the negative of the vector v2, and negative just means flip its direction. That's all. v2 and minus v2, they are exactly equal in magnitude. They are different only in the direction. So if v2 is, let's say, 5 units, then minus v2 will be minus 5. And this minus here just means that it's going to the left, and plus v5 means it's going to the right. So vector subtraction, you do not have to learn it separately from vector addition. Once you know vector addition, and as long as you understand that vector subtraction is the same thing as adding the negative of a vector, then you do know vector subtraction as well. Of course, you have got to know what is a negative vector. What does negative vector mean? And all it really means is flip the direction. Whatever is the direction of a given vector, to get its negative vector, flip the direction. Alright? Alright. Moving on to the next slide. On the next slide, we are going to look at different ways to add vectors. Broadly speaking, there are two methods to add vectors. The first one is the graphical method, also known as geometric method. And the second one is the analytical method, which is also known as the component method. Now this graphical method of vector addition, this is going to be the major topic of this lecture. Analytical method of vector addition, we're going to cover it in the next lecture. There are different ways to add vectors graphically. The first one is the triangle method, also known as head-to-tail method. Why is it called as head-to-tail method? You will see it in a few minutes. The next one is the parallelogram or tail-to-tail method of vector addition. And last is the polygon method of vector addition. Now this polygon method, it is basically a generalization of the triangle method of vector addition. So in today's lecture, we're going to look at these three different methods to add vectors. We're going to look at them conceptually. We're going to work out their mathematics, and we're going to look at some examples. So you ready for it? I am. Let's begin it. The first graphical method or the geometric method to add vectors is the triangle method or head-to-tail method of vector addition. What does it say? It says that if two vectors are represented by two sides of a triangle in sequence, their resultant, that is the sum of these two vectors, is the third side of the triangle taken in the opposite order. Now, what do these words mean? Let's understand it with the help of a picture. Like this say, a picture is worth 1,000 words, or is it 1,000,000 words? I forget how many words, but certainly a picture can convey a lot more than words can. So let's look at these two vectors over here, vector A and B, and we want to add them. We are going to add these two vectors A and B using the triangle method, also known as tail-to-tail method of vector addition. So in the triangle method of vector addition, what we are going to do is we are going to grab this vector B. Okay, so you grab this vector B and you move it parallel to itself. Okay, here. So what you basically do is you grab this vector B and you move it parallel to itself. That means like this. See, I'm moving this vector B parallel to itself here on the screen. By moving parallel to itself means I'm not changing the orientation of this vector. I'm not changing the angle of this vector. So you move this vector B parallel to itself until the tail of vector B, it coincides with the head or the tip of vector A, like this. That's all I did. Move vector B parallel to itself until its tail coincides with vector A. You see that? Okay. Next, to get the sum of these two vectors A and B, we are going to draw a third vector that's going to originate at the tail of vector A and it's going to end at the head of vector B. So that is going to be something like this. So something like this here. This pink line, this is resultant vector R. It is equal to A plus B. Here I have already shown it to you, but I couldn't let go of another opportunity to draw diagrams over here. It's so much fun, and I hope that you're also drawing these things on your own notebook while I'm teaching this to you. Why? Because, like I always say in every single lecture, I say it. Math and physics, these are not spectator sports. You're not going to learn them by watching them. You actually have to do the things by your own hands. You actually have to derive things. You actually have to write down the formulae, and you have to solve problems to learn these things. And hopefully you're doing those things. All right. Moving on. Same thing, triangle method, head to tail. Now, why is it called head to tail? Because here is the head of vector A, and this over here is the tail of vector B. So you're going from the head of the first vector to the tail of the second vector. And the third vector, it's going to go from the tail of the first vector to the head of the second vector. So this over here is basically just a repetition of what we just did on the last slide. We are adding vector B to vector A. That means move vector B parallel to itself until its tail coincides or its tail touches vector A's head. All right, we did that. After we drew vector A and vector B in sequence, we're going to draw a third vector R that goes from the tail of vector A, the first vector, to the tip or the head of the second vector, vector B. Now on the next slide, we're going to change the order of the things a bit. We're going to do B plus A instead of doing A plus B. That means we're going to move vector A parallel to itself until the tail of vector A coincides with the head of vector B. Very well, we do that. And then we draw a third vector going from the tail of vector B to the tip of vector A and call that vector as R prime. And that is equal to B plus A. Now look at this R and R prime. What difference do you see between them? All right, it's not fitting very well on the screen. I can fix that for you. Here we go. Let's see. We're going to take vector R prime and make its copy. Okay, here's what I did. I made a copy of vector R prime. Now let's go ahead and change its color. Why? Why not? Make it red. Now we're going to move this vector R prime parallel to itself. And aha, watch this. It is equal to vector R. There's no difference between R prime and vector R. You see that? What does this tell us? It tells us something very, very important, and that is it doesn't matter if we add A to B or B to A. The order of the two vectors does not matter in case of triangle method of vector addition. Taking it further. Alrighty. Same image, looking a bit prettier, at least to my eyes. So what we're saying is that vector R, it is parallel to vector R prime. They're not only parallel, they are actually identical. They are equal to each other. Here, vector R is equal to vector R prime. And if vector R is equal to vector R prime, what does that give us? Vector R, which is equal to vector A plus B. This is vector R. It is equal to R prime. R prime is equal to vector B plus A. That means A plus B equals B plus A. So what it means is this. So let me put it here that vector R is not just parallel to, but it is equal to vector R prime. It tells us that vector addition is commutative. Vector addition is commutative. What does that mean? It means you can swap the order of the two vectors without affecting the resultant sum. We're beginning with a diagram for triangle law of vector addition, where we are adding two vectors A and B, and we have the resultant vector R drawn. Next thing what we're doing is we are drawing a vector parallel to vector B. Okay. Not just that, we also added another vector A parallel to vector A. So this gives us parallelogram law of vector addition. Parallelogram law of vector addition kind of follows from the triangle law of vector addition. I showed you step by step how we drew this parallelogram. You saw that. We began with triangle law of vector addition, and then we added two parallel vectors. And what do we end up with? We end up with the parallelogram. And this vector R, the resultant vector R, it is the diagonal of the parallelogram. So here, triangle law of vector addition, also known as head to tail method, is number 1. Then we have parallelogram number 2 here. We could represent this diagram of parallelogram law of vector addition in one more way. Begin with vector A plus B here. This is A plus B. And this over here, what is this? This is B plus A. Then you join these two together. And when you join them, you get this thing. So here, once again, the parallelogram law of vector addition, it follows from what? It follows from the triangle law of vector addition. Except here in this case, the tails of the two vectors are joining. Therefore, it is called as tail-to-tail method. So here's what you do for parallelogram law of vector addition. You take two vectors. So you move the vectors parallel to themselves. You can move just one vector while holding the other fixed, or vice versa, or you can move them both without changing their angle, without changing their orientation in the space, and bring them close to each other till they join tail to tail. Something like this. Something like this. Join them tail to tail. And then construct a parallelogram using these two vectors as the two consecutive sides of a parallelogram. Then the resultant of the sum of those two vectors is the diagonal of the parallelogram going through those two vectors' tails. That means if I draw this diagonal in pink color, this will be wrong answer. This is not going to be the correct resultant of vector A and B. The resultant has to go through wherever the tails of those two vectors join. So it has to be this. Parallelogram law of vector addition. There we go. Like this. Now what do we do next? We complete parallelogram using these two vectors as two adjacent sides of a parallelogram. So forgive me if I don't make a very good parallelogram here. I'm not an artist by any means. Here we go. Call it good enough. So the resultant will be this diagonal. This diagonal that is going through the two vectors tail over here. That's all there is to it. It's very simple. I mean, it flows naturally from the triangle law of vector addition. There's nothing much to it. Now, if you want, you could move it to the origin of the coordinate frame. Might make your life easier. And then complete your parallelogram and draw the resultant vector. So this was your parallelogram law of vector addition. What are you doing here? You put two vectors tail to tail. Do not change their angle. If you change the angle of the vector, it's not the same vector anymore. Then you have changed the vector. Okay. Construct a parallelogram using these two vectors as two adjacent sides of the parallelogram. I'm not going to write it all down, but if you're writing down your notes, you should write it down. Draw a diagonal going through where the tails of the two vectors join. Here you go. Then you know this diagonal is the resultant of the two vectors when they're added. Now so far, whether we discussed triangle law of vector addition or we discussed the parallelogram law of vector addition, how many vectors have we added? 2. But in reality, we may have to add more than 2 vectors. If we have to add more than 2 vectors, is there any kind of graphical method that we can use to add more than 2 vectors? Sure is. And that is our third and the last kind of graphical method of vector addition, the Polygon law of vector addition. Let's look at that next. Moving on to the Polygon law of vector addition. Like we said, if we want to add more than 2 vectors using graphical method of vector addition, then we hire Polygon law of vector addition. So Polygon law of vector addition, what it says is this: if you have multiple vectors that are represented as consecutive sides of a polygon, drawn in the same order, then the resultant is represented by the closing side of the polygon drawn in the opposite order. A lot of words. What do these words mean? Let's understand with the help of a picture. So here we go. Vector A. Add to it vector B. Head to tail. To that, add a third vector C. Again, tail of C is at the head of vector B. Then vector D. Tail of vector D is at the head of vector C. We want to add these 4 vectors. So what we want is vector A plus vector B plus vector C plus vector D. We want to add these 4 vectors. So what we have done, we have put them head to tail, head to tail, head to tail, head to tail. Doesn't matter how many number of vectors you have. Put them all head to tail in sequence. So this is what's happening. You began over here. This is your initial position. Let's label that as I. Then you went along path segment A, then B, then C, and then D. So the initial position is I. Then there's vector A plus B plus C plus D. And over here, this is our final position. Now let's pretend for a second that these vectors, these are displacement vectors. So if A, B, C, and D, these are displacement vectors, and you began at I, that is the tail of vector A, and you ended up at the tip of vector B, that is F. How do you find the net displacement? Yep, you're right. You find the net displacement by drawing this straight line from I to F. There you go. This is our resultant vector R. And in terms of the diagram, what do we see? We have a polygon here. And the vectors that we are adding, these are consecutive sides of the polygon taken in order. That means head to tail, head to tail, head to tail. Keep on going head to tail for as many number of vectors as you have. And then at the end, you close that polygon by drawing a vector that originates, that begins at the tail of the first vector, which is vector A. For this case, going to the tip or the head of the last vector, which in this case is vector D. And this vector, which forms the closing side of the polygon, taken in the opposite order, that is the resultant vector. See that? I mean, it's very simple. There's not much to grapple with here. So, here we go. Resultant vector R. Very well. Once again, a quick review. What we just did is the polygon method of vector addition, using which we can add more than 2 vectors. If we are adding only 2 vectors, then that is the triangle law of vector addition. So this over here This is the generalization of the triangle law of vector addition. So here you go. Generalization of triangle method of vector addition gives us polygon method of vector addition. Very well. Polygon method. We have added vector A, B, C, and D in sequence. What's happening in the next diagram? In this diagram, instead of adding A, B, C, D in sequence, now we are adding A, C, B, and D in sequence and drawing the vector R. And in the last one, we are now adding D to C to B to A. Now see once again here. In 1, we have R is equal to A plus B plus C plus D in this order. For the second diagram, we're again using the polygon method of vector addition, but here we are adding vector A to that vector C to that vector B and then lastly vector D. So we have swapped the order of vector B and C here. Okay, and then the last one, we're reversing the order of all the vectors. But as you can see, the resultant vector R is same for all three cases. That means the order of the vectors, it does not matter even for the polygon method of vector addition. What is this property called as? This property is called as the commutative property of vector addition. You can change the order of the vectors and the resultant is going to remain the same. This property is called as the commutative property of vector addition. Let's go back here. Okay, so I have come back to the slide. I want to discuss it a bit more. So here we are adding 4 vectors. We see that. Let's do one thing. Let's first add vector A and B only using the triangle law of vector addition. And if we did that, what would we get? We will get this vector over here, right? Let's call that as R1. Okay. So now after we have done that, vector A and B, they're gone. We have gotten their resultant vector R1. Next what we will do is we will add this R1 to vector C using triangle law of vector addition. Why? Because now R1 and C, these are head to tail. They are placed head to tail with each other. So let's go ahead and add R1 to vector C and we get this vector R2. Now we see that R2, it is head to tail with vector D. Let's go ahead and add vector R2 to vector D. And when we do that, what do we get? We get vector R. So basically, polygon method of vector addition, it is the triangle law of vector addition repeated several times. If you're adding 4 vectors, then you're using triangle law of vector addition 3 times. If you were adding 7 vectors, then you will be using triangle law of vector addition how many times? Yes, 6 times. If you're adding n number of vectors, n vectors, then you could use triangle law of vector addition n minus 1 times. And that would be equivalent to polygon method of vector addition if you added all of the vectors together at once. Now we said that these are graphical methods of vector addition. The easiest way to do is to begin at the origin. Wherever the vector is, you could move it. You can move it parallel to itself until its tail is at the origin. So when you're adding multiple vectors, the first one, move it to the origin of the coordinate frame. And that makes it easier to measure the angles because then the angle will be with respect to the positive x-axis. It's easier to do it, right? You see that? I hope you do. Alrighty, moving on. My goal is to keep this lecture mostly qualitative, but this is physics, and without mathematics, physics is incomplete. So we're going to put a little bit of mathematics in here. And what we're going to do is, we're going to find the resultant of the vector addition for just 2 vectors mathematically. Why just 2 vectors? Because just like I showed you, you can reduce addition of any number of vectors to just 2 vectors. Like when we added 4 vectors using polygon method of vector addition, we could add two vectors at a time. How? Like I showed you here. We could reduce it to adding two vectors at a time and add the resultant to the next vector and so on. So here what we are going to do is find the value of the resultant of sum of two vectors, vector A and vector B. So that means when we add these two vectors A and B and get the resultant, this resultant R, we want to find the magnitude and the direction of this resultant vector R. So let's go ahead and do that. Before we start working on it, what is given to us? We are given vector A and vector B. That means we know the magnitude and direction of these two vectors. So of course we want to keep the orientation of the vectors unchanged in the space. But what we could change is our coordinate frame. We could rotate it. That means, so if these are our x and y axis, right? And over here, this is our vector A. Then what I'm saying is that I cannot change the orientation of vector A. But what I could do is I can rotate my xy coordinate frame such that vector A is now going to align along the positive x-axis. In other words, move this coordinate frame a little bit over like this. So now our x-axis, it will be this. This is our x-axis and this will be our y-axis. We are free to do this. Nobody is stopping us from doing this. So what's the benefit of doing this? Now vector A, it is going to be at angle 0 degrees with x-axis. And vector B, whatever angle it makes with vector A. So look here, this is extension of vector A here. And vector B is making angle theta with vector A. So this angle theta is now also made with x-axis because we have placed x-axis along vector A. Or we have placed vector A along x-axis, right? So this resultant vector R, whatever angle it will make, it will be with the x-axis. And we want to find it. So you will see that if we rotate the coordinate frame such that vector A now lies along the positive x-axis, you will see that it makes the mathematics and therefore life much easier. So here we go. Once again, we are given vector A and vector B. That means we know the magnitude of vector A and magnitude of vector B and the angle between them, which is angle theta. Okay, what do we want to find out? We want to find the magnitude of vector R, which is the resultant of the vector sum of vector A and vector B, and we want to find out the angle that vector R makes with x-axis in this case. So let's do it. We will begin by labeling the vertices of the triangle as O, P, and Q. Next thing that we're doing is drawing this vertical line from vertex Q. And wherever the extension of vector A intersects with this vertical line from point Q, we're going to call that point as point D. So let's do one thing. Let's make space here. All right, so what are we doing? We want to find the value of R. So if we take right angled triangle OTQ, now we're going to use Pythagorean theorem in this right angled triangle. What is the hypotenuse of this right angled triangle? That is OQ. So OQ squared equals height. Height is QT. QT squared plus OT squared. Now OT is made of two segments, OP plus PT. OP is equal to magnitude of vector A. And PT, let's leave it equal to PT. So OT is equal to A plus PT. Now on the left side over here, in this formula over here, OQ is equal to magnitude of the resultant vector R. So OQ squared, it is equal to R squared, equal to QT. QT is QT, leave it as QT, QT squared plus OT squared. That will be equal to A plus PT. Square it. What does this give us? QT squared plus, now we're going to square A plus PT. That gives us A squared plus PT squared plus 2A times PT. Okay. We said that we know the magnitude of vector A, which is just A. We know the magnitude of vector B, which is just B. And we know the angle theta. Okay. So we want to find this vector R's magnitude in terms of magnitude of vector A, magnitude of vector B, and or angle theta. Those are the three quantities that we know. So what are we going to do? Let's go to triangle QPT. This is also a right angled triangle. And in this right angled triangle, sine theta, that is going to be equal to what? QT divided by QP. Okay, this is equal to QT divided by QP. QP is magnitude of vector B. What does this give us? This gives us sine theta is equal to QT divided by B. Now let's go ahead and multiply it by B on both sides. So this B on the right hand side, it cancels out. What do we get? We get QT is equal to B sine theta. So what we're going to do is, in place of this QT, we're going to plug in B sine theta. Since we have QT squared, we get B squared sine squared theta. Let's go ahead and put it in here. Plus A squared. Now this PT, let's try to write PT in terms of what's known to us, and that is A, B, and theta. All right, back to triangle QPT, cosine theta. Cosine theta is equal to PT divided by hypotenuse QP, which we know is equal to B. And this will give us PT is equal to B cosine theta. So here, so PT squared, that will be equal to B squared cosine squared theta plus the last term. The last term that we have is 2A times PT. Let's leave 2A as 2A and PT. PT will be equal to B cosine theta. So what do we get? We get this B squared and this B squared, okay, times sine squared theta plus cosine squared theta. So what have I done? This is what I have done. I'm combining this term over here with this term, okay? So in these two terms, B squared is common. I've factored it out. Inside, I'm left with sine squared theta from here and cosine squared theta from here. All right, moving on. Then I have this plus A squared. Let's write it down. Then I have plus 2AB cosine theta. Would it fit here? Sure would. 2AB cosine theta. Now we're going to invoke the identity sine squared theta plus cosine squared theta equals 1. What does that give us? That gives us B squared times this. This is equal to 1 plus A squared plus 2AB cosine theta. So you can see for yourself that in this case, if angle theta was equal to 90 degrees, okay, that is if vector A and vector B, they were at right angle to each other, then this cosine theta will be cosine 90 degrees, which is equal to 0. And in that case, R squared will be equal to B squared plus A squared. Simple Pythagorean theorem. All right, so this is the square of the magnitude of the resultant R of the vector sum of vector A and vector B that are at angle theta to each other. Now, this is the square To get r from it, what do? Square root of both sides. What does that give you? Let's write it down here. Vector r is equal to square root of a squared plus b squared plus 2ab cosine theta. So like we said, in this case, we know the magnitude of vector A. Square that magnitude, you get a squared. We do know the magnitude of vector B. That gives us b squared. And we do know the angle theta between vector B and vector A. That's it. Done with the magnitude of vector R. Now we're going to figure out angle alpha that R is making with the positive x-axis. In this case, where we have aligned vector A along the x-axis. Or even if you didn't do that, this angle alpha, it is the angle that the resultant vector R is making with vector A. Alright, let's do it. Now we want to find out the value of this angle alpha. How do we do that? To figure out the value of angle alpha, let's begin with right-angled triangle OTQ. Tangent alpha, that's going to be equal to QT divided by OT. Now this OT in the denominator, we're going to write this as sum of OP and PT. Let's go ahead and do that. QT divided by OP plus PT. Now here we could do tangent inverse of both sides and find the value of angle alpha. However, we said that we want to find angle alpha and magnitude of vector R in terms of the known variables, and those are magnitude of vector A and B, the angle theta between them. Now we do not know QT and we do not know PT. OP is equal to length of vector A. So what we're going to do is we're going to write QT as equal to QP sine theta divided by, let's leave OP as OP. PT will be equal to QP cosine theta. What does this give us? QP is equal to magnitude of vector B sine theta divided by OP. OP is magnitude of vector A plus QP, magnitude of vector B, cosine theta. Here's what we got. So here we go. Tangent alpha is equal to B sine theta divided by A plus B cosine theta. What we're going to do next is this. Take tangent inverse of both sides. We get alpha is equal to tangent inverse of B sine theta divided by A plus B cosine theta. If you're given numbers for vector A and vector B, it's just a matter of plugging numbers into the equation, putting into your calculator or in your head, however you like to do it, and getting the answer. It's as simple as that. There's really not much to it more than this. Like I said, we're going to look at a couple of problems in this lecture, just not yet. We're first going to look at some properties of vector addition. The first one, we have repeated it a few times during this lecture, that vector addition is commutative. What does it mean? That means the order of vectors in the vector addition does not matter. A plus B is same as B plus A. If you wanted, you could have put any number of vectors here. A, B, C, D, F, G, H, whatever you want. However many. And scramble the order as much as you want. It would not affect the resultant. That is the commutative property of vector addition. Simple? Simple. Next is the associative property. What does that mean? That means this. If we have, let's say, vector A plus vector B plus vector C, or as many vectors as you want. Let's say you went ahead and added these two vectors first, vector A and B, and got the resultant R1. And then you added that to vector C. And you will get some resultant, let's call it as R. Okay, that's our scenario number 1. In comparison, if you had done this instead, what? Let me write it down for you. A plus B plus C. Now what we're going to do is, let's add B and C first. Okay, that gives us some R2. Then R2, now we add that to vector A. This addition, this is also going to give us vector R, same as this one. This is the associative property. Now if you want, you could have added vector A and C first, and then added vector B to that. That would give you the same answer. So this is the associative property of vector addition. Next one, additive identity. What does that mean? That means for every vector, there is such a vector that when added to the vector, does not change the vector. So there's one kind of vector. When you add it to any vector, the identity of that vector to which it is being added is not changed. And this is a, what kind of vector? What did you say? You learned about it in the last lecture. A null vector. Also known as what kind of vector? Zero vector. So zero vector is a vector when added to any vector does not change the identity of the vector. You could subtract it from any vector, you could add it to any vector, and it would not change a thing. Now the question is, why do we need it? We need it because if you subtract a vector from itself, what would you get? A zero vector. All right. Hopefully that made sense. Moving on, additive inverse. That means for every vector, there is a vector that when added to it gives a zero vector. So what can you add to a vector such that the result is a zero vector? Of course, negative vector. So negative vector of a vector is its additive inverse. Okay. Moving on, last is the closure property. Closure property says that when you add two or more vectors, whatever result you get, that is going to be a vector as well. It just means that the offsprings of humans are going to be offsprings. Offsprings of dogs are going to be dogs. Same way, if you add two or more vectors, or if you subtract two or more vectors, then the resultant is going to be a vector. You're going to remain in that vector space. That's the closure property. Okay, so next we are going to move on to a couple of problems. Very, very interesting problems. Problem number 1. What are the properties of two vectors, A and B, such that when you add these two vectors, okay, you get a vector C, and magnitude of vector A plus magnitude of vector B equals magnitude of vector C. So here's what it means is this. You are adding two vectors A and B, and that is equal to third vector C. And also the magnitude of vector A and magnitude of vector B is equal to magnitude of vector C. So what we're saying is that vector C is the resultant of the vector sum of vectors A and B. Just a few slides ago, we saw that vector R was equal to what? Square root of A squared plus B squared plus 2AB cosine theta. And this is under the square root. So in this case, we will have vector C equal to A squared plus B squared plus 2AB cosine theta. This is the magnitude of vector C. But we are told that magnitude of vector C, it is equal to A plus B. So when will this square root be equal to A plus B? It will be equal to A plus B when theta is equal to 0 degrees. When theta is equal to 0 degrees, cosine 0 degrees is 1. What will this become? A squared plus B squared plus 2AB. Why? Because this cosine theta will be equal to 1. So this A squared plus B squared plus 2AB, that is equal to a plus b squared, right? So now you have square root of a plus b's square, which is equal to a plus b. Is it too tight here? Okay, I could do better than that. Let me quickly show it to you one more time. So what we're saying is this here. C is equal to a squared plus b squared plus 2ab cosine theta. This is square root. So this is the generic formula for magnitude of the resultant vector C, which is vector sum of vector A and vector B. But now in this case we're given that magnitude of vector C equals magnitude of A plus magnitude of B. Okay, so these left sides are equal to each other. That means right side must also be equal to each other. When will they be equal? They will be equal when theta is equal to 0 degrees. Okay, when theta is equal to 0 degrees, what do we get? We get a squared plus b squared plus 2ab cosine 0 degrees, right? Square root. This is equal to a squared plus b squared plus 2ab. Cosine 0 degrees is 1. What does this give us? Now this a squared plus b squared plus 2ab. This is nothing but a plus b's squared. Now there's another square root outside. So square root cancels out this 2. And what are you left with? A plus b. So that means this condition is met when theta is equal to 0 degrees. This implies vector A is parallel to vector B. Hopefully it was simple and easy enough for you to see. But I do understand that many of you might be doing these things for the first time, and you may have some questions. I know this is not a face-to-face class, but please do know that I'm here to help you. So if you have any questions, please do let me know in the comments. All right, moving on to part B. Part B says vector A plus B is same as vector A minus B. When will this be true? When will A plus B be equal to A minus B? This will be true when B is equal to a 0 vector. You can add or subtract a 0 vector from any vector and it wouldn't change a thing. So when vector B is a 0 vector, vector B has to be a 0 vector. Here you go. Simple. All right, part C. A plus B is equal to C in terms of vectors, and A squared plus B squared equals C squared. So we just saw that C is equal to A squared plus B squared plus 2ab cosine theta under the square root. So we want C to be equal to A squared plus B squared. Okay, and here's C squared. So that means up here, if I square this, then we get rid of this square root. What does this give us? The C squared equals C squared. Left side is same. That means right hand side must be also same. That means this A squared plus B squared equals A squared plus B squared plus 2ab cosine theta. Subtract A squared from both sides. Subtract B squared from both sides. So here you go. B squared cancelled. A squared cancelled. Same on the right hand side. What does that give us? That gives us 2ab cosine theta is equal to what? 0. But neither 2 is equal to 0, nor A is equal to 0, nor B is equal to 0. That tells cosine theta has to be equal to 0. So if cosine theta is equal to 0, that gives us theta is equal to 90 degrees. That means when two vectors A and B, they are at right angle to each other, then A squared plus B squared equals C squared, as we expect from Pythagorean theorem. So this was kind of conceptual question. Not too easy, not too hard, but it was kind of a cute question and I liked it. So I wanted to do it for you guys. Moving on to problem number 2. In this problem number 2, we have a vector A with a magnitude of 10 units and is directed west. Okay. Then we have a vector B that is directed 45 degrees east of south and has a magnitude of 6 units. Alright, we're asked to construct vector diagrams to calculate a plus b and a minus b. And furthermore, estimate the magnitude and directions of a plus b and a minus b from your diagram. Alright, so let's go ahead and write down what is given to us. Let's write it down in terms of diagram as the problem has indicated us to do. First thing, we have a vector A that has magnitude of 10 units and is directed west. So here we go. Let's call this as vector A. And it is 10 units. It's going west. So going west means it is going in the negative x direction. Alright. The second vector B, it is directed at 45 degrees east of south. We know that going straight down, this is south. Going to the right is east. So what we want to do is we want to go 45 degrees east of south. Vector B, it is 6 units. Now these arrows, they're not drawn to scale. Next thing we want to do is construct vector diagram to calculate a plus b and a minus b. Let's focus on a plus b first. Now to find a plus b, let's use triangle law of vector addition. What do we do in triangle law of vector addition? We keep the first vector where it is. We take the second vector and move it parallel to itself until the tail of the second vector, it coincides with the head of the first vector. So here we go. We have now placed vectors A to B, head to tail, as the triangle method asks us to do. How do we find the resultant of A plus B? Let's call that resultant as vector R1. How do we find R1? To find this R1, which is equal to A plus B, we're going to draw a third vector. Let's call that as R1, going from the tail of the first vector to the head of the second vector. Here's our R1. And what does it equal? It equals vector A plus vector B. Alright, so here you go. We have constructed vector diagram to calculate A plus B. But we are not done yet. We are next going to estimate the magnitude and directions of A plus B. Just a few slides back, we looked at how to determine the magnitude and direction of vector R1, that is a vector sum of two vectors, A and B. And it was equal to, here this is magnitude of vector R1, it equals A squared plus B squared plus 2AB cosine theta. And we're going to put it under the square root. Now these A and B, these are magnitudes of the vector A and B respectively. And this theta over here, this is the angle between vector A and vector B. We know that vector A, it is along the negative x-axis. And we know that vector B, it is 45 degrees south of east or east of south. East of south. Alright. That tells us this angle that vector B, it is making with the x-axis, it is 45 degrees. To get the angle between vector A and vector B, what we are going to do is, we're going to extend vector A here. This is an extension of vector A. And over here, this is our vector B. So the angle between vector A and B, or any two vectors, is the angle that they make with each other when they're placed tail to tail. Here we go. So this angle would be what? It would be 180 degrees minus 45 degrees. That is 135 degrees. So here we go. Now we have all the information that we need to calculate magnitude of R1. Let's go ahead and do that. A is 10. 10 squared is 100. B is 6. 6 squared is 36 plus 2 times A, which is 10, times B, which is 6, times cosine of 135 degrees. Put it under the parentheses and raise it to power of 1/2. What do we get? Let's go ahead and add this 100 to 36. That gives us 136 plus 2 times 10 is 20. 20 times 6 is 120 times cosine of 135 degrees. And this whole expression is raised to the power 1/2. So we get 136 plus 120 times cosine 135 degrees. This is equal to minus 84.8528, keeps on going, parentheses closed, to the power 1/2. I'll make this equal to 136 minus 85 to the power 1/2. What does this give? And this gives us square root of 51. Okay, let's make some room here. Square root of 51. This is equal to approximately 7 units. So here we go. R1's approximate value, 7 units. Hopefully you know that these two squiggly lines, these means approximately. Here we go. Are we done now? No, we're not done yet. We have determined the value of the magnitude of the vector R1. We do not know the value of the angle theta that this R1 makes. Now we want to find out what angle does this R1 make with the positive x-axis, like this. So let's do one thing. Let's make a fresh diagram to figure out what angle does the resultant makes with the x-axis. Like I said, these diagrams, they are only approximately drawn. They're not drawn to scale. Okay, so this is the diagram that we have. What we want to find out is, let's say this is our positive x-axis. What angle does the vector R1 it makes with the positive x-axis? Let's call that as equal to phi. So we want to determine the value of this phi. Some people like to call it as phi, some people like to call it as phi. Doesn't matter what you call it. It remains the angle that vector R1 is making with the positive x-axis in this case. Now there's definitely more than one way to solve for this angle phi. You can use whatever method you like. The method that I like to use is the law of cosines. What is law of cosines? Hopefully you already know that. If not, then I encourage that you look it up. So using law of cosines, what I'm going to do is, I'm going to determine the value of this angle over here. What shall I call it? Let me call it as alpha. So law of cosines is going to let me determine the value of alpha. And once I know the value of alpha, then phi is equal to what? 180 degrees minus alpha. Knowing the value of alpha, I can easily determine the value of phi. Let's go ahead and do that. So law of cosines, that's going to say that b squared equals a squared plus r1 squared minus 2a r1 cosine alpha. So here, we're interested in finding the value of this alpha over here. And alpha is a part of this cosine. So what we want to do is we want to isolate this cosine alpha. How do we do that? For that, we are going to add 2a r1 cosine alpha to both sides of this equation. All right. And not just that. we're going to subtract b squared from both sides of the equation. And when we do so, what do we get? We get 2a r1 cosine alpha equals a squared plus r1 squared minus b squared. Now, next thing we're going to do is divide both sides of this equation by 2a r1. What does that do? It gets rid of this factor 2a r1 that is multiplying cosine alpha, and we're left with only cosine alpha on the left hand side, and that is what we want. So let's go ahead and do that. Cosine alpha equals a squared plus r1 squared minus b squared divided by 2a r1. Now you may have noticed that I have not plugged in any numbers here yet. It's a good idea actually to hold off putting in numbers until you have your expression in almost the final form. It just saves you so much hassle. Why? Because many times, not in this case, but many times, a lot of the symbols, they end up canceling each other out, or the expression might simplify so much that it will save you a lot of work if you did all the calculation at the end. And not just that, we will make more rounding off errors if we start plugging in numbers from the get-go. So avoid doing that. But now is a good time to plug in our numbers. So let's go ahead and do that. A is equal to 10. 10 squared is 100 plus. We said R1 was equal to approximately 7. So 7 squared is 49 minus b squared is 6 squared, 36 divided by 2 times a, which is 10, times r1, which is 7. What do we get? We get 113 at the top, and at the bottom we'll get 140. And this is equal to cosine alpha. What do we do next? You're right. We're going to take the cosine inverse of both sides. And when we do so, the left-hand side will be equal to alpha on the right-hand side. We get cosine inverse of 113 divided by 140. What do we get? Now, before you plug in these numbers into your calculator, make sure that your calculator is in the correct mode. Here we want our answer for the angle in degrees. So make sure that your calculator is set in degrees. This is equal to approximately 36 degrees. This is the value of alpha. But what we actually want is the value of phi or phi. I don't like to say phi because it reminds me of like fees for something. And I'm absolutely not in the mood to pay fees for anything. I'm working hard toward establishing a life of minimalism right now. I don't know if I'll succeed, but hey, I'm trying. 180 degrees minus. Minus what? Minus alpha. Okay. So here once again, I should not put this equal sign. I should, well, no. Over here it should be equal. The next one should be approximation. 180 degrees minus 36. What does this give us? This gives us 144 degrees. This is the answer. So here we go. We have solved for part 1. We have figured out the value of R1 and its angle. So how about I put it as theta R1. Theta R1, which is the angle that the vector R1 is making with the positive x-axis, is equal to 144 degrees. Here we go. So like we said, in the second part of the problem, we're interested in calculating a minus b. Let's call a minus b equal to R2. Okay. Now we know that vector a it is 10 units long going due west. So here's our vector A. It is 10 units long. I'm just not writing units here to keep the diagram clean and simple. Vector B. Vector B is 6 units long and it's going 45 degrees east of south. So this is our vector B. Now what hint did I give you? I said that to solve for A minus B, you have to flip the direction of vector B. Let's do one thing. Let's take this vector B and make its copy. So here we go. This is going to be our vector minus B. All I have done is this. I copied the vector B and then I flipped the direction of the arrow. So I went from vector B to minus B. As simple as that. Next thing that I'm going to do is I'm going to call this vector minus B as a new vector. Let's call that as vector C. By doing so, what happens is this. A minus B. It changes to A plus, oops, not A plus oops, A plus C. Now all we have to do is simple vector addition. A plus C. How do we do that? Very simple. We want to put A and vector C, head to tail. This is our vector A. I brought it down. Maybe I brought it a little too down. All right. Bring vector A here. Now we want to add vector C to vector A, head to tail. That means tail of vector C, it is going to coincide with the head of vector A. So all I have done is I have moved vector C parallel to itself until its tail coincides with the head of vector A. So here you go. Now you tell me, how would you draw the resultant R2? The resultant R2 will be a straight line arrow drawn from the tail of vector A to the head of vector C. Here we go, R2. Let's go ahead and talk about the angles here. If I extend this vector C, something like this, then I know that this angle over here, this is 45 degrees. That means this over here will be 135 degrees. Now what did we say? To determine the angle between two vectors, you have to place them tail to tail, okay? So any two vectors, it could be, let's say, any random vector here, call it as vector x, and some other random vector, vector y. If you want to determine the angle between these two vectors, place them tail to tail, like this. And here, this is your angle that vector x and vector y, they make with each other. So we want to do the same thing here. We want to determine the angle between vector A, which is this one over here, and vector B, which is this up here. But these are placed head to tail. We want to place them tail to tail. Well, we don't really have to literally do it. What we could do is go ahead and extend this vector A. Okay. This is the extension of vector A. That means if vector A had been any longer, it will go in this direction. Then the angle between vector C is this one over here. This is vector C. This is the direction of vector A. This is the angle between the two. What would it be? It will be equal to 45 degrees. Are you with me so far? Angle between A and C. That is equal to 45 degrees. Let's call that as theta. Why not? And now we are going to repeat the same procedure that we did for the part 1 of this problem. To determine the value of R2, simply use this formula that says R2 is equal to A squared plus C squared plus 2AC cosine theta, where this theta here, It is the angle between vector A and vector C. All right. Put it under the square root. What do we get? All right, let's go ahead and plug in the numbers now. A is 10, 10 squared is 100. C is 6, 6 squared is 36. Plus 2 times A, which is 10, times C, which is 6, times cosine 45 degrees. How is it 45? This angle here. This is 45 degrees. This is the angle between vector A and vector C. Okay, now if you remember, in the last problem we had 135 here. 135 degrees means it is in the second quadrant, and cosine in the second quadrant is negative. However, now this cosine 45 degrees, it is in the first quadrant and it's going to be a positive number. So you will see that overall, this value should be much larger than the value for R1. In the last case, A plus B, we had cosine 135 degrees, which made this entire term a negative term. So this number, it's a smaller number for R1 than it is for R2. All right, let's go ahead and see it. So 136 add up to give us 136 plus 2 times 10 times 6, 120, cosine 45 degrees. Square root. Now I'm going to use my calculator to figure this out. This is going to be equal to 136 plus 120 cosine 45 degrees. This is equal to 84.85, so on. So I'm going to round it up to 85. Here we go, 85. What do we get? This is equal to now 221. Square root of 221. Square root of 221 is 14.86606875. I'm going to round it up to 15. So here we go. We have the value of the magnitude of vector R2. It is 15 units. Let's go ahead and put it over here. 15 units. Next, we want to find the value of the angle that R2 makes with the positive x-axis. Last time we called it as phi. This time let's call it as beta. Why not? So what I'm going to do is I'm going to invoke law of cosines again and solve for this alpha. Once I know the value of alpha, then beta is simply equal to 180 degrees minus alpha. So let's go ahead and solve for alpha using law of cosines. How do we do that? Watch this. So law of cosines. This says c squared equals a squared plus r2 squared minus 2, okay, let's make some space here, 2a r2 cosine alpha. So now we want to isolate this cosine alpha. And to do that, add 2ar2 cosine alpha to both sides and subtract c squared from both sides of this equation. And when you do so, what do you get? This is what you get. You get 2ar2 cosine alpha. This equals a squared plus r2 squared minus c squared. Now we're going to divide both sides by 2ar2. That will isolate cosine alpha. So we get cosine alpha, it equals a squared plus r2 squared minus c squared divided by 2ar2. Now we're going to plug in the values of a, r2, and c in the right hand side of this equation. What do we get? We get a squared is 100 plus r2 squared is 225 minus c squared is 36 divided by 2 times a. What's the value of a? 10 times r2. r2 is 15. Okay, what do we get? We get 100 plus 225 minus 36. This equals 289. So here we go. 289 divided by. We have 2 times 10 times 15. This is equal to 300. We have cosine alpha. Now here, if you ever get this fraction on the right hand side to be greater than 1, then you should immediately know that you have made a mistake. Why? Because cosine alpha, its value lies between -1 to +1. It will never be less than -1 and it will never be greater than +1. So the number that you get here, this fraction, this should never be smaller than -1 and never be greater than +1. And we are good here because 289 divided by 300, it's a positive value that is less than 1. Now we're going to take cosine inverse of both sides and figure out the value of alpha. So alpha equals cosine inverse or arc cosine of 289 divided by 300. This is equal to 15.56 degrees. What we want to find is the value of this beta. Beta is equal to 180 degrees minus alpha. Let's go ahead and calculate it. 180 degrees minus alpha, and we said alpha is equal to what? 15.56 degrees. What does this give us? That gives us beta equal to 164.44 degrees. Let's approximate 164.44 to 164 degrees. So here we go. Now we have determined the angle and the magnitude of the vector R2. Its magnitude is 15 units and its angle is 164 degrees. This is the angle, this 164 degrees that vector R2 is making with the positive x-axis. So here we go. We have solved for vector R2, which is a minus b. So just a quick recap. In this lecture, we looked at graphical methods of vector addition. And these graphical methods, they are of 3 kinds. We have triangle method of vector addition. We have parallelogram law of vector addition. And lastly, we have Polygon law of vector addition. These 3 are not too different from each other. The second and the third, the parallelogram law and the Polygon law, kind of flows from the triangle law of vector addition. As we have seen in this lecture, as long as you understand basic mathematics and the triangle law of vector addition, then you can certainly figure out the math for parallelogram law of vector addition and Polygon law of vector addition, because parallelogram law of vector addition is basically same as the triangle law of vector addition. In the parallelogram law of vector addition, if we have 2 vectors, something like this, vector A and vector B, then to get the resultant of the sum of these 2 vectors, here, this is vector R. Now this right hand side of the parallelogram, it has same dimensions as the vector A. It has same length as vector A. Here, this is an extension of vector B and vector A is going this way. So this angle here, this is the angle between vector A and vector B. So using the same formula that we have learned, where R is equal to A squared plus B squared plus 2AB cosine theta, you can figure out the value of R. Or you could have used the law of cosines. If you want to use law of cosines to determine the value of R, then you have to use this angle, which is 180 degrees minus theta. And if you use law of cosines, here we'll have a negative sign and we'll have 2AB cosine 180 degrees minus theta. And these numbers over here, they will remain the same. Now we know the identity. Which identity? The identity that cosine 180 degrees minus theta is equal to negative cosine theta. So these two are basically the same things. There's absolutely no difference between these two formulae. So you can see very clearly that once you understand the triangle law of vector addition, and you can do its mathematics, you can do the mathematics of parallelogram law of vector addition and the Polygon law of vector addition. Because Polygon law of vector addition, it is a generalization of triangle law of vector addition. For Polygon, you have to apply triangle law several times in sequence. This is what I mean. Let's say, here you go, your vector 1. Here you go, your first vector A, second vector B, third vector C, fourth vector D, fifth vector E. And what you're trying to find is vector R, which is equal to A plus B plus C plus D plus E. Here. How would you determine it? Vector R is the straight line that is going from the tail of the first vector, vector A, to the head of the last vector, vector E. If you wish, you could split this problem into multiple parts. So first figure out the sum of A and B, that would be R1. Then you go ahead and figure out the sum of vector C and R1, and this will be your R2. In part 3, you're going to figure out the sum of R2 and D, and that would be vector R3. And lastly, figure out the sum of R3 and E, and that would be vector R. So here you go. Let's write it down. Vector R1, it is equal to A plus B. In the next step, you're going to add this R1 to what? R1 will be added to vector C. What does it give us? That gives us vector R2. Then go ahead and add R2 to D, and that gives us vector R3. Lastly, add vector R3 to vector E, and that gives us vector R, the final R. So you can see that Polygon law of vector addition is basically, it's a triangle law done multiple times. If we have n number of vectors that are being added, then the triangle law will be applied n minus 1 number of times to figure out the resultant. Or if you were using a graph paper, then you could simply draw vector R. Just take a ruler and draw vector R, and using a protractor, measure the angle of vector R, and using the ruler, measure the length of vector R. So it can be done without mathematics by using simply a ruler and a protractor. Hope that made sense.